This is question 10 from the first CSAT sample paper. And what we're told is we've got a circle touching the parabola y equals x squared at two places, and the radius of the circle is r. The angle between the two radii, joining the centre to these points of intersection, is 2 theta. So this angle here I've drawn as theta. We're asked to find r in terms of theta. Bear in mind, in drawing this picture, I've assumed that the centre of the circle is on the y-axis, so that the situation is symmetric. So your geometrical intuition should probably tell you that, given the situation described. If you want to have it explained why this is the case, then I'll explain that at the end. But for the first part, we'll just take it as read that it's symmetric, so the centre of the circle is in the middle. In any case, given this, if you want to have a go at this question yourself, pause the video now. Okay, so supposing the circle looks like this, how are we going to proceed? There's an easy way and a hard way. And the hard way would be to think about the intersection of the two curves, so the fact they're intersecting. So we could write down an equation for the circle, although we don't actually know the y-coordinate of the centre, so that would have to be an unknown. And then we could set it equal to this, and try to find where they intersect, and then somehow find r in terms of theta from there. But in this case it says the two curves touch, and that means that we also know something about the gradients. Their gradients are equal at this point. And if we try and write down equations for their gradients, those are going to be simpler than the equations of the curves themselves, because this is just going to be 2x instead of x squared, so we're not squaring for the gradient. And also, to work out the gradient of this line is actually quite easy. And we know a fact about tangents to a circle, so we can work out the gradient here if we know about this radius. And it makes sense that in terms of gradients we're going to get something in terms of theta, because that's an angle, the angle of this radius. So it makes sense we'll get something in terms of theta straight away instead of having to do any working. So what we're going to do is to think about the gradients at this point. Okay, so first I'm talking about the curve, and I say the gradient of the curve here is 2x, so that's the derivative, so the gradient is 2x. We don't know what x is here because we haven't worked out where the curves intersect, but we only need it in terms of r and theta. And what is x in terms of r and theta? It's just the distance from the y-axis, so it's this horizontal distance here, and we can see that's just going to be r sine theta because it's that line opposite this angle theta. So that means the gradient is 2r sine theta. And now let's try and get this gradient a different way so we can relate r and theta. So let's talk about the gradient of this radius here. So if we're looking at the gradient of this radius, we just want difference in, or change in y over change in x. So you could actually do this just in terms of angles, but let's do it the normal ways in terms of difference in y over difference in x. What's the difference in y? It's this distance here. So if you think of this as a right angle triangle, this distance here is r cos theta, but we want it to be negative because we're going down. And then this distance here is r sine theta, as we said already. So that means the gradient of this radius is minus r cos theta, going down r cos theta, over r sine theta, because we're going to the right, r sine theta. And as you can see, the r's will cancel, so that's just minus cot of theta. So now we have everything we need to relate r and theta, because we've got two expressions for, well, this isn't an expression for the gradient of the curve yet, but you can see this is going to be related to that, and it's only in terms of theta, whereas this has an r, so we can set two things equal and get r in terms of theta. So if this is the gradient of the radius of the circle, what expression does this give us for the gradient of the curve? Well, the thing to know is that the tangent to the circle is normal to this. It's the right angle to this. So the gradient is minus 1 over this. And the tangent to the circle, because it's touching the curve there, if we just go up, the tangent to the circle has to have the same gradient as the curve at that point, because if two things touch, they have to have the same gradient. So that means that once we find the gradient of the tangent, that should be the same as the gradient of the curve. So we can say what the gradient of the tangent is there. It's minus 1 over cot, which is tan. Or sorry, minus 1 over minus cot, so the minuses disappear. And we just get tan. So we can say 2r sine theta equals tan theta. And now it's useful to remember that tan theta is sine over cos. So we've got a sine both sides and we can cancel. So on this side we just get 1 over cos, and then we can divide through by 2. We get r is a half. 1 over cos is just sec, so we get a half sec theta. Or you can remember that tan over sine is sec. So r is a half sec theta, and that means we have r in terms of theta. So we're done. Okay, so now let's think about why the centre of the circle has to be on the y-axis, which we assumed from the beginning, and it seems natural, but it's not that easy to show. I think the easiest way is actually to go algebraically. So let's think about the equation of the circle. Suppose we don't know its centre. So that means the equation of the circle, we can just say is x minus a squared plus y minus b squared equals r squared. So a and b are unknowns. R is given to us, that's fixed. And suppose we were looking for it to intersect, or for it to touch the curve. Then to find the point of intersection, what we could do is substitute in x squared for y, because we know if it intersects the curve, then y is equal to x squared. So we can substitute in x squared there, and then we get a quartic in x. We're getting powers of x squared and x from here. We're getting x to the 4 and x squared from here, and then some number term. But because we know the circle touches the curve here, and it touches in 2 points, where it touches, suppose it touches at the points alpha and beta. Because it's touching rather than crossing, that means we know there's a double root there. So that means we know if we solve the equation, well, alpha is a double root, so x minus alpha squared is a root, and likewise x minus beta squared is a root. We can set that equal to 0. And we know that our 2x coordinates are going to be the 2 solutions of this as well as the 2 solutions of this. So when we rearrange this and make a quartic, when we expand this out and get a quartic, they should be the same quartic. So that means we can compare coefficients. And when we do that, I won't go through the algebra. When we do that, we see this has no x cubed coefficient. And that means from here, when we look at the x cubed coefficient, we get that beta is equal to minus alpha, or alpha is equal to minus beta. So that means these are opposite sides of the y-axis. So alpha is just a reflection of beta in the y-axis. And from there you can immediately see that the centre of the circle is going to be at the origin. You can also work it out algebraically by looking at the x coefficients of both of these. And seeing that the x coordinate of the centre has to be 0. So that's a way of algebraically showing that the centre of the circle has to be on the y-axis. But since in this question you weren't asked for a proof, this isn't necessarily a part of your answer, as long as you can see that the circle will have to be centred there.